My name is Nathan Welker. I'm on a team with Skyler Crowther, and for our project, we analyzed a solar water evaporation system and compared experimental data with analytical data derived using heat transfer equations. This evaporation system was the result of a project of a previous class. It uses lenses that focus sunlight onto a trough of water. The water is evaporated and then collected in a water collection system. No analytical model has been derived to estimate flow rates through the system. Therefore, the purpose of this project is to create an analytical model that accurately represents the system. Sunlight shines instantly on and through the lenses situated at the top of the system, which heats and evaporates water. The water condenses on the underside of the lenses and is collected. As was shown in the previous slide, 12 lenses are arrayed and focused on a basin of water. The evaporated and condensed water runs down the side of the system and is collected. This collected water can be measured to get an accurate flow rate. However, not all the sunlight reaches the water, as some is reflected back into the atmosphere. There are also fluid and heat losses in the system, which will be discussed later. In order to correctly model this system, these losses will need to be taken into account. In order to quantify these values, a heat transfer energy balance needed to be performed. A theoretical mass flow rate of the evaporated water can then be calculated from this energy balance. In order for this system to be quantified, however, a few assumptions needed to be made. First, the water trough was assumed to be an unstable horizontal flat plate, and Nusselt values under these conditions were calculated in order to find the heat transfer coefficient H. The second assumption is that the control volume was assumed to be the water trough itself, and the third assumption is that only convection losses were considered. These assumptions allowed an equation to be derived. As was discussed in previous slides, only a portion of the sunlight reaches the water. Because acrylic is used on the top of the system, its absorptivity value of 0.9 was used to calculate the amount of solar radiation reaching the water in the trough. These values provided the energy in term in our energy balance. The energy out term is the losses of the system, which is only convection as stated in our assumptions. There are two energy storage terms in this system, one accounting for the temperature change of the water and another accounting for the phase change of the water. Data of the solar irradiation and wall temperature of the system were collected and implemented into the energy balance equation in order to determine the theoretical mass flow rate of the system. These data were collected during experimentation in order to accurately match our experiment. Using a solar meter, solar irradiation was measured at half-hour increments. Due to the experiment being performed in the morning, the irradiation slowly increased over time. An infrared thermometer was used to measure wall temperature, which is assumed to be the environment temperature of our system. This wall temperature was also measured at half-hour increments and, also due to the experiment being performed in the morning, slowly increased over time. Due to these changing values of the data over time, the average of these values was used in the calculations. Knowing the initial temperature of the water and implementing the assumptions made, a theoretical mass flow rate of 4.14 times 10 to the minus 5 kilograms per second of water was calculated. An experiment of the system was performed, and a mass flow rate was determined by taking the difference between the initial water volume and the final water volume. As was mentioned in the first slide, there were some fluid losses in this system. The system leaked water, and therefore there was no way to trust the measured values of volume that came out of the system. Therefore, the only way to accurately measure the evaporated water was to measure the initial and final water volumes and then take the difference between the two. After performing the experiment and leaving our system out in the sun for 2 hours, a final water volume was found to be 50 milliliters, which equates to 9.040 times 10 to the minus 6 kilograms per second of water that was evaporated by the system. In conclusion, a correction factor is needed in order to accurately represent the flow rate of evaporated water through the solar water evaporation system. The error of the experimental mass flow rate when compared to the theoretical mass flow rate was equated to be 78.2%. While this error is large, it was expected due to the losses of the system. Therefore, by multiplying our equation by this correction factor, or 1 minus the error, which is 0.218, a model that accurately describes our system under the assumptions made is derived. If more time was allotted for this project, further experimentation could be completed to verify this model. However, the model fulfills the purposes of this project and the purposes of our system. Thank you.